Hello everyone, myself Yogita, and today I'm presenting on transmission electron microscopy and scanning transmission electron microscopy. So let's discuss the history involved with electron microscopy first. So with J.J. Thomson's electron discovery, the stage was set for future developments in electron-based technologies. Then in 1924, with de Broglie's wave particle duality theory, scientists were able to understand and harness the behavior of electrons, that a particle like electron along with associated momentum has also wavelength associated with it, and that too very shorter wavelength. So it was thought that electron could be used to image objects at much higher resolution than the optical microscopy. But the problem was how to converge this beam of electrons to a focus. Then in 1926, Hans Busch he introduced magnetic lenses, and the idea was basically to use the force of magnetic fields to focus this beam of electrons, because electrons being charged particles, they could be focused using this magnetic field. So after this, by exploiting this wave-like nature of electrons, the scientists were able to invent electron microscope, which was capable of achieving very high resolution, far beyond the optical microscopy. So in 1931, Ernst Ruska and Max Knoll they invented first electron microscope, which used electromagnetic lenses. And then in 1933, they constructed the first stem, which was capable of transmitting electrons through the thin specimens, by revealing their intricate details. So, what is the principle behind the transmission electron microscopy? That so there, like, let's understand what happens when incident beam falls onto the sample. So, electron can either just get back scattered or reflected, but it can also interact with the sample and can eject out an electron from the inner shell, creating a vacant orbital, which will be filled by electron present in higher shells uh, while generating X-rays. Also, there are possibility of generating Auger electrons after secondary processes, but electron can simply pass through the sample undifracted, or it can get scattered away elastically or inelastically. So the idea here is to utilize these transmitted electrons, undifracted or scattered, these electrons, to utilize these electrons in order to obtain the image of the sample. So what is the information that we obtain from TEM is we can get to know the internal structure of the sample, its morphology, the basically the chemical composition, the structure of the crystal, how the atoms are arranged. So all that information we can obtain using TEM at nanometer scales. So samples like biological specimens or nanomaterials can be used for imaging in this type of microscopy. So in the instrumentation, there is electron gun on the top, which is the source of electron beam, and gets this electron beam gets accelerated towards the anode and then is made to fall on this condenser lens, where the size and angular spread of the electron beam is being controlled, and then this electron beam falls onto the specimen, and then the transmitted electrons are they fall on this objective lens, then the intermediate lens, and on the projector lens. This intermediate and projector lens is just to magnify the size of the image, and then finally obtain the image on this fluorescent screen. Types of electron guns. There are sources of electrons like tungsten filament or lanthanum hexaboride. We can eject electron out of these sources by providing them enough energy so that they can cross that surface barrier. So depending upon the source of energy we are providing these electrons, there are two different kind of electron guns. In field emission electron gun, energy is supplied using electric field, whereas in thermionic electron gun, energy is supplied using heat. The field emission electron gun is used when we require high resolution, because the electron beam that is produced using this gun has more electron intensity. Let's discuss the illumination system. What is its purpose? So this A figure, this illumination system, where the electron beam is passing through the C1 lens and then to the C2 and then through this aperture and falling onto the specimen. This is the illumination system. Here we try to illuminate the sample homogeneously, like we want the illumination to be homogeneous, and the C2 aperture, it is used to adjust the beam current. Like we do not want to damage our specimen, so the intensity of the beam can be controlled using this aperture. And this figure B is the imaging system, where after what it is indicated what happens after the beam passes through the specimen. So it goes from the specimen to the objective lens and then passes through the objective aperture and then selected area aperture, and then it falls onto the intermediate and projector lens, which are basically just magnifying the image, and finally you obtain the image on the screen. In TAM imaging of the specimen, it needs to be taken care of that the sample is thin enough so that it can transmit electrons through it. It needs to be electronically transparent. Here we take specimen as a 3mm disc, which is mounted on a specimen holder. This rod like device is a specimen holder. It has O-ring on it, which creates a tight seal and also secures the sample and isolates it within the TAM column tube. And these are the grid holes on which we mount our samples, and using different mesh discs available with different mesh sizes. These are the different mesh discs which are available in different mesh sizes. Sample is mounted on the sample holder using these mesh discs. If the sample size is even smaller than the size of the mesh, then a thin coating of amorphous carbon is done on this mesh disc so that it doesn't fall into the TAM vacuum. And therefore we can use this mesh discs to support our sample on this specimen holder. So before mounting the sample onto the specimen holder, we need to make sure that the specimen is like electronically transparent, is a thin sample. So how do we actually prepare that level of electronic transparency? So for that, we first reduce the thickness up to 0.1 millimeter by some mechanical techniques like grinding, or we can use dimple grinding. So this hand grinding jig is used to reduce the thickness uniformly, keeping the planes still parallel to each other. So the sample is placed in the center where it is written as S, and this G, the guard ring, is responsible for the final thickness, uniform thickness of the sample. Here the dimple grinding is used, which basically reduces the thickness from the center of the specimen, and then final thinning takes place. So these two mechanical techniques can be used to reduce the thickness up to 0.1 millimeter. For final thinning, we can use electrolytic thinning. This can be done only for materials which are electrolytically conducting, like metal specimens. So we can electrolytically reduce the thickness of samples which are electrically conducting. So what happens is we can use jet polishing, where we place the sample in a specimen holder and sample acts like an anode, and both the sides of this sample are exposed to jet electrolytic stream, which also serves as a cathode. So this dissolves this anode, because anode is oxidizing and getting dissolved into this electrolyte, so therefore reducing its thickness. And this process goes on until light transparency is detected by light detector. So yes, this is a really good way to reduce the thickness, but it is only for electrically conducting materials. Ion milling, whereas, is used for samples which are not good electrical conductors. So what happens here is the specimen is placed after dimple grinding on the molybdenum mesh and is made to bombard with high energy ions, which knocks atoms out of its surface and therefore reducing its thickness. And this process goes on until the light transparency is detected by these light detectors. And while this process goes on, there is a lot of heating, so liquid nitrogen is used to cool down the system. In ultramicrotomy, what we do is we place our sample on this holder, and we gradually, and this is the knife, very sharp edged knife placed on this knife carrier, and this holder is made to come closer to this knife while it is repeatedly moving up and down. And when it comes into contact with this knife, the knife gradually sections the specimen. That's how we get our final thinned sample. So this technique is used for specimens, biological specimens or polymeric specimens. Now that we've discussed techniques for different techniques for final thinning, there are some other unique techniques used for different kind of materials. Like hammering can be used for ductile metal such as gold, cleaving can be used for mica and graphite, and chemical thinning can be used with suitable acids for non-metallic materials. Or for ceramic specimen, we can extract them by precipitating or separating them. And now that we have discussed how to prepare the specimen or how to mount it, now we are in the position to understand the different image modes in the TEM. So what happens is that when the electron beam interacts with the sample, it may either get just simply transmitted through it, or it can get scattered away. So depending upon the difference in the number of electrons in the scattered beams, we see that there is contrast in the image screen. So scattered electron can create images with two different mechanisms. One is the mass density contrast, so the other is diffraction contrast. So because of the difference in thickness and density in a specimen, uh, it will generate variations in electron intensity received by an image screen in TEM. So this mass density is observed in samples like amorphous polymers or biological specimens, and it can be increased by staining. So what happens after staining is that when we stain a sample, it increases its thickness and density. Therefore, there will be low scattering observed there and low intensity observed on the screen. What is diffraction contrast? Because of diffraction, we see that there is less electron density that is being received on the image screen from this side, because these planes are in accordance with the Bragg condition. So there is diffraction observed here, and because of that, it is being blocked by this aperture, and there is low intensity in the image screen. So because of the diffraction, we see that there is contrast that is observed in the image screen. So diffraction contrast can generate bright field and dark field. So how can it generate is when we allow the transmitted beam to pass through the aperture, we see bright field imaging. But if diffracted beam is allowed to pass through the aperture, dark field imaging is observed. So these are the selected area diffraction pattern. Such a pattern is obtained by diffraction from a selected area in the specimen that contains a single crystal. So basically we are limiting the area which is contributing to the diffraction pattern. These are the two different images we can see. The A image is the bright field image and B is the dark field image. So resolution is the ability of TEM to distinguish two closely spaced objects as separate entities. So it is limited by two factors, like diffraction can limit resolution, and the aberrations like chromatic aberrations, spherical aberrations can definitely limit the resolutions. So this is a formula for resolving power. Here this n sin alpha is numerical aperture, and n is the refractive index of the sample, and alpha is the Sami angle of the convergence of magnifying lens. What happens is when we increase the aperture alpha, the resolution also increases, but because of the lens aberrations, it only increases up to an optimum value. After that, it starts decreasing. So because of this lens aberration, the resolution is limited, and also because of the diffraction, it is limited. Magnification refers to the apparent size of an object compared to its actual size, while resolution, it should not be confused with. Resolution refers to the ability to distinguish between two closely spaced objects. Magnification can be formulated as Li upon Lo, where Li and Lo are the distance of image and object from the lens. Depth of focus is the range of specimen thickness over which the image remains in focus. It can be mathematically formulated as 2s upon beta, where s is the spot size. We can see in the left side image where s is the spot size and beta is half of this alpha angle. Beta is semi-angle of beam convergence. In this diagram here with pink cone, we can see high numerical aperture, which indicates very high resolution, but depth of focus here is very low. And with this blue cone, we see low numerical aperture, but depth of focus is very high. So these two have reciprocal relationship. We'll have to compromise with either of these. Either depth of focus can be increased or resolution can be increased. So let's see how acceleration voltage affects the resolution. So when acceleration voltage increases, the resolution also increases, and when it decreases, the resolution decreases. Sometimes we just don't want high resolution images because of unclear surface structure, and there is more charge up, more damage of the sample, so we rely upon the low resolution. But we can see these images, as we increase the acceleration voltage, the resolution increased. In all these images we can see the difference very clearly. Scanning transmission electron microscopy, STEM. In this technique, electron beam is made to fall on the sample at just one point rather than falling homogeneously on the entire sample, and then this focused beam is then scanned all over the sample, therefore giving us multiple signals at the same time. The samples which are used to visualize their structure and their composition are tissue sections, lamella, and nanoparticles. Different kind of detectors are used in STEM technique, like bright field detectors, annular dark field detectors, half angle annular dark field detectors, depending upon the angle of the scattering angle of the electrons. We can see in TEM the specimen is being illuminated upon as parallel beams, but in STEM the electron beam is converged or focused at one point on the specimen. So this is one major difference between TEM and STEM imaging techniques. Uses of STEM. In STEM, images are built up pixel by pixel by scanning the beam across a fixed field of view using scanning coils. This technique can be paired with different other spectroscopic techniques to provide even more information, like elemental composition and electronic structures. So it just not only identifies the atomic structure but also detects the individual dopant sites. This technique is very useful, and it is used to study semiconductor interfaces, heterogeneous catalysis, biological sciences, and it is also used in even more studies. So TEM and STEM, these are the two techniques which gives us information like morphology, their composition, atomic structures, crystal arrangements, and a lot of information we can obtain using STEM and TEM both. Thank you.